Just the other day, while the existential terrors pursued me, I was thinking, our decimal system sure is great. With merely 10 symbols, 0 through 9, we can represent all the numbers we could ever please. Being the decimal system, of course, it's based in the number 10. So a number like this, 4528, is representing 8 copies of 10 to the 0, 2 copies of 10 to the 1, 5 copies of 10 to the 2, and 4 copies of 10 to the 3. And while this sure does seem great, while sitting in my blissful state of reflection, I realized there's one big problem, and that is the country of Canada and its 10 provinces. You see, in the country of Canada, it's too ding-dang cold all the time, and so they had to introduce these things called negative numbers to represent the temperatures. Negative numbers exist to the left of 0, and you can see that our 10 digits in the decimal system are not sufficient to express these wacky negative numbers. In fact, we have to introduce this new symbol called a minus sign, or a negative sign. And so I sat, kicking my feet and wondering what could be done to rid us of this abominable symbol. Well, it only takes a little thought to realize that a number system doesn't have to use base 10 like ours does. For example, we could use a base 3 system, which is called ternary. In the base 3 system, a number like 221 is representing 1 copy of 3 to the power of 0, 2 copies of 3 to the power of 1, and 2 copies of 3 to the power of 2. That's 9 plus 3 plus 1, or 13 in our familiar base 10 system. But still, no matter what base we use, base 10 or base 3 or base 2, 6 or 60, we're still not going to be able to express negative numbers without that pesky negative symbol. We need something a little bit more clever. And it turns out there is a way around this after all. Instead of using a decimal system, which is base 10, we can use what's called a
Negadecimal
system, which is base negative 10. With a real lark of a system like this, the negatives are basically encoded in the base system itself, and it's not going to be necessary to use negative signs to represent negative numbers. In fact, we'll be able to express positives and negatives alike without a single negative sign. Let's see an example of the incredible
negadecimal
system in action. Consider the number 1906, and I'm going to put in the subscript negative 10 to indicate that this is written in
negadecimal.
Now, what is this equal to in our standard decimal system? Well, let's apply what we know about number bases and see if we can compute it. This 6 is representing 6 copies of negative 10 to the power of 0. This 0 is representing 0 copies of negative 10 to the power of 1. This 9 is representing 9 copies of negative 10 to the power of 2, and this 1 is representing 1 copy of negative 10 to the 3. Just as in our more familiar base systems, the powers of negative 10 increase by 1 with each digit. Then, if we write these pieces out in our decimal system below, we see that the 6 is representing 6 copies of 1, the 0 is just representing 0 copies of negative 10, the 9 is representing 9 copies of positive 100, because negative 10 squared is positive 100, so that would be plus 900. And then this 1 is representing 1 copy of negative 1000, because negative 10 cubed is negative 1000, so that's minus 1000. 900 minus 1000 is negative 100, plus 6 is negative 94. So in fact, this number, written without a minus sign in
negadecimal,
is equal to negative 94 in our standard base 10 system. And so, with a quirky system like this, we can move beyond this stupid glorified hyphen. And just like with positive bases, the negative base doesn't need to be 10, it could be 2 or 3 or anything else we like. Let's do one more example in
negaternary.
This is a base negative 3. So what does the number 2102 represent in
negaternary?
Well, this first 2 is representing 2 copies of negative 3 to the power of 0. This 0 is representing 0 copies of negative 3 to the power of 1. This 1 is representing 1 copy of negative 3 to the power of 2. And this 2 is representing 2 copies of negative 3 to the power of 3. So in total, writing out the pieces in decimal, this is 2 times 1 plus 0 times negative 3 plus 1 times positive 9 plus 2 times negative 27, so minus 54. See how we're able to get positives and negatives with this system because the digits alternate from representing positives to representing negatives. The even powers, like the power of 0 and the power of 2, are representing positive quantities, while the odd powers, like the power of 1 and the power of 3, are representing negative quantities. Adding these things together, we get a result of negative 43 in base 10. Again, we see a negative number written without a minus sign. And if you'd like to live your life from now on without those meddling minus signs, you'll be relieved to know that the conversion process is not too difficult. Let's consider how we would write negative 348 in the decimal system as a
Negadecimal.
number. All we have to do is perform a simple division algorithm, repeatedly dividing by the desired base, which in this case is negative 10, and noting remainders. So consider negative 348 divided by negative 10. You might be tempted to say this is 34 with negative 8 left over, but we want our remainders to be positive. So in fact, we would say that this is equal to 35 with the remainder of positive 2. 35 times negative 10 is negative 350, plus 2 gets us to negative 348. 35 here is called the quotient, and we need to take these quotients and continue this process iteratively. So we would now take 35 and divide by negative 10. In this case, the quotient is negative 3. Negative 3 times negative 10 is positive 30, which of course produces a remainder of positive 5. Finally, we take this quotient of negative 3 and divide it by negative 10. And again, since we need positive remainders, we would have a quotient of 1, that's negative 10, and then a remainder of 7 to bring us up to negative 3. And then at last, we would take that quotient of 1, divide that by negative 10, which is going to give us a quotient of 0, which is our sign to stop, with a remainder of positive 1. Then, to get your brand new
Negadecimal.
expression for this decimal number, just take these remainders in reverse. That is, our answer is 1752 in
Negadecimal.
well, this is just great. We've spent so much of our lives dealing with negative signs when all this time it was simply unnecessary. Now we can take this new
Negadecimal.
system forward with arithmetic and everything we like. Let's give it a try and perform some
Negadecimal.
addition. Consider the numbers 34 and 89 in
Negadecimal.
I'm going to omit the subscripts of negative 10 here. Let's just know that these are
Negadecimal.
numbers, and let's try adding them together. Indeed, this is an elementary procedure which your average concussed rat could perform. 9 plus 4 is 13, so that gives us a 3, carry the 1. 1 plus 3 is 4, plus 8 is 12, so that gives us a 2, and carry the 1. We get a final answer of 123 in
Negadecimal.
now, I don't want to be like a nerd, but I feel like maybe we should just double check this real quick. If we were to quickly write these
Negadecimal.
numbers in base 10, 34 is negative 26 base 10, and 89 is negative 71 base 10. So the sum we calculated, if we convert it to decimal, should be equal to negative 97. Well, let's just run the numbers here real quick to be sure. This is representing 3 copies of negative 10 to the power of 0. This is representing 2 copies of negative 10 to the power of 1. And this is representing 1 copy of negative 10 to the power of 2. So in total, it's 100 minus 20 because of 2 copies of negative 10, and then plus 3. That, of course, is equal to 83, which does not match what it's supposed to.
Shit.
Well, so unfortunately, life is a complex network of negatives and sacrifice. We can't just frolic along merrily without the minus sign and pretend like nothing else has changed. We do have to be a bit careful about this addition. So what has gone wrong here? Well, let's consider the negative tens place. 3 copies of negative 10 plus 8 copies of negative 10. That's what gave us this carry. If we have 3 copies of negative 10 plus 8 copies of negative 10, that is of course 11 copies of negative 10, which is the same as 1 copy of negative 10 plus 10 more copies of negative 10. It's these 10 copies of negative 10 which we carry into the next
Negadecimal.
place. The problem is that next place value is negative 10 squared, as in positive 100s. But 10 copies of negative 10 is not positive 100, it is of course negative 100. So in fact, because the
Negadigits.
alternate sign in
Negadecimal.
the carries need to be negative. The same thing of course happened here with the 4 and the 9. This carry shouldn't have been 1, it should have been negative 1. That's because 4 plus 9 does give us 10 plus 3, but this next place value is representing negative 10s, so our positive 10 would need to be represented as a negative. So in the end, the negative of that carry, along with the negative of the place value, would cancel out, giving the positive 10 that we actually wanted. If we carry out this
Negadecimal.
addition with the negative carries, we will get the correct answer. 4 plus 9 is 13, so we have 3, carry a negative 1. Negative 1 plus 3 is 2, plus 8 is 10, so put down a 0 and carry a negative 1. Now this is a little tricky because we are in the negative 10 squared, or positive 100s place, and all we have is a negative 1. We of course can't put negative 1 down as the digit, but we need to write something that will have the effect of taking away 100. The way we do that is by adding 100 by putting a 9 in the hundreds place, and then subtracting 1000 by putting a 1 in the minus 1000s place. In total, you could run the numbers yourself, but if you convert this to decimal, it will be negative 97, as it should be. Now, historically, the use of negative base systems has been pretty scarce. A guy named Vittorio Grunwald introduced them at first in 1885, including instructions on how to perform a lot of basic arithmetic in these quirky negative base systems. Since then, they have been introduced independently a few other times and have occasionally been implemented on computers. So while the negative base systems haven't yet caught on, they do certainly get the job done. It is possible to write any number you like in a negative base system. Here's another question to ponder. Could there be a number which is written the same way in base 10 and base negative 10, or any other similar pair of positive and negative bases? The answer, of course, is yes, because, for example, 10 squared is the same as negative 10 squared, so both decimal and
Negadecimal.
have a standard hundreds place value. As a result, if we write 100 in base 10, this represents positive 100, and if we write 100 in base negative 10, this also represents positive 100. And of course, just like the 10 squared place is the same as the negative 10 squared place, the 10 to the 0 and negative 10 to the 0 places are the same as well. Those are just the units in decimal and in
Negadecimal.
which is to say we could change this units digit to anything other than 0, it could be 1 through 9, as long as we match it in decimal and in
Negadecimal.
and this equation would be preserved. Differences, of course, would start to occur in the second digit, because in decimal that represents tens, whereas in
Negadecimal.
that represents negative tens. We talked about addition, but what about subtraction? Unfortunately, that's a bit of a pain in
Negadecimal.
as well. Let's consider 34 minus 89. I'm sad to say that it will be advantageous to write a minus sign in front of each of the
Negadigits.
We already have a minus sign in front of 8, let's also put one in front of 9. Then we do the addition digit by digit. 4 plus negative 9 is negative 5, and 3 plus negative 8 is also negative 5. Of course, we can't have negative 5 in the ones place, so we need to do something that's equivalent to taking away 5 units. To do that, we're going to add 1 to the negative tens place, and then we can put 5 in the units place. In that way, we've subtracted 10 by adding 1 to the negative tens place, and then we've added 5 back in the units, so in total we've subtracted 5, which is what we needed to do. Now 1 plus -5 gives us -4 in the negative tens place, and we've got to worry about that, because we can't have -4 either. Of course, -4 in the negative tens place is the same as adding 40, so to add 40, what we'll do is put a 1 in the hundreds place, that's adding 100, and then put 6 in the negative tens place, that's taking away 60, 100 minus 60 in total is positive 40. And so we arrive at the result of the subtraction. 34 minus 89 in
Negadecimal
is 165. If you're curious what all of this was in base 10, 34 is -26 base 10, 89 is -71 base 10, and so when we subtract these, we're actually adding 71 to -26, and so the result in base 10 is positive 45. One interesting use case of
Negadecimal
is to consider weighing things on a scale. Suppose all of our weights are powers of 10 and we want to weigh out 281 grams. Perhaps there's a tiny little frog on the other side of the scale, and so he's the fella that we're trying to weigh. Well, if he weighs 281 grams and all of our weights are powers of 10, we're going to need quite a few weights. To get to 281, we would need 2 big 100-gram weights. We would then need 8 10-gram weights, and then we would need a weight of a single gram. And think about the body image issues this frog is going to have when he sees this many weights used on the other side of the scale just to measure him. The situation is not hopeless, for if only we could use both sides of the scale, the negadecimal system would give us an easy way to see how to weigh out 281 grams. Indeed, if we are able to use both sides of the scale, then the powers of 10 that our weights represent could be both positive and negative. Then we need only note that 281 in decimal is equal to 321 in
Negadecimal.
This
Negadecimal
representation tells us exactly how to weigh out 281 grams on this balanced scale. The positive powers of 10 should all go on the same side, so these 3 copies of 100 and 1 unit should go on, let's say, the left side of the scale. There are 3 hundredweights and 1 little gram. And then the 2 representing 2 copies of -10 tells us we just need to put 2 of those 10-gram weights on the other side of the scale. Then the left side has 301 grams, but 20 of those grams are being countered by these 2 blocks on the right side of the scale. So when we plop down our frog on this right side, things will balance out evenly. Well, I'm glad we have that settled, but to leave these more serious issues behind for a moment, let's consider unique representations. Famously, our positive base systems lack unique representations of numbers. For example, in decimal, 1 is the same as 0.999 repeating. As another example, 0.5 is equal to 0.4999 repeating. We could also represent 3 as 2.999 repeating, but this trick of representing an integer using an infinite sequence of 9s does not work in
Negadecimal.
because, of course, such a sequence of 9s in
Negadecimal
would have positives and negatives and positives and negatives. It wouldn't be quite so simple. As a result, integers like 1 and 3 and -5, integers have only a single unique representation in
Negadecimal.
That's pretty cool, though it is perhaps more interesting to consider how we might construct 2 representations of a single number in
Negadecimal.
if indeed that's possible. Well, it turns out it is possible. I'll walk you through a particular example in
Negadecimal.
from which it's pretty easy to construct the general rule for these sorts of representations in any negative base. So first, let's consider the
Negadecimal
number 0.09 repeating. What does this represent if we write it out in our decimal system? Well, this first
negadigit
of 0 is 0 copies of -10 to the -1, because it's 1 spot to the right of the
Negadecimal.
point. And then that 9 is representing 9 copies of -10 to the power of -2. And that 0, 9 pattern continues, 0, 9, 0, 9, 0, 9, and so on. So next we would have 0 copies of negative 10 to the power of negative 3, and then 9 copies of negative 10 to the power of negative 4. This goes on forever, and what you can see is that we have 9 copies of the even negative powers of negative 10. Negative 10 to the negative 2, negative 10 to the negative 4, and so on. The odd powers are matched up with those zeros, so those will disappear from the sum. Since all of the even negative powers of negative 10 have a factor of 9, we could also take that factor of 9 out, and thus write it in this
more simple form
of 9 multiplied by negative 10 to the negative 2, plus negative 10 to the negative 4, and so on. Those of you who've learned a little bit of calculus may recognize this as what's called an infinite series, which is really what we're dealing with anytime we have an infinite repeating decimal. In particular, this is what's called a geometric series, because each term in the sum has a constant ratio with the term before it. For example, to get from this term to this term, we would multiply by negative 10 to the negative 2. To get from this term to this term, we would again multiply by negative 10 to the negative 2. Because that ratio of negative 10 to the negative 2 is constant, this is again called a geometric series. We can write an infinite sum like this more succinctly using what's called sigma notation. And that looks like this. For the first term in the sum, we would plug in I equals 0, giving us negative 10 to the negative 2. For the next term in the sum, we would plug in I equals 1, giving us negative 10 to the negative 2 minus 2, which is negative 10 to the negative 4, and so on. This goes on, of course, to infinity. Of course, the negative 10 to the negative 2i is changing as I increases from 0 to infinity, but there is also the negative 10 to the negative 2, which we could take out of the sum by itself. Negative 10 to the negative 2 is 1 over negative 10 squared, which is 1 over 100. So we could pull that out as 1 over 100, thus in total, we would have 9 over 100 outside of our sum. What would remain in the sigma is the sum of negative 10 to the power of negative 2i from I equals 0 to infinity. At this point, we can use the geometric series formula. Because the common ratio is negative 10 to the negative 2, which is a number between negative 1 and 1, we can evaluate this infinite sum using this formula, which either you recall or you'll just have to take my word for. Remembering to keep that 9 over 100 outside of the sum, the formula tells us that this geometric series is equal to 1 divided by 1 minus the common ratio, that common ratio being negative 10 to the negative 2. We can then just multiply these fractions. In the numerator, of course, we have 9 times 1, which is 9. In the denominator, 100 times 1 is 100, and then remember, negative 10 to the negative 2 is 1 over 100. So when we multiply that by 100, we would just get 1. Thus, in the denominator, we have 100 minus 1. In total, this is 9 divided by 99, which is 1 divided by 11. So this is the value of that infinite repeating
negadecimal
number we wrote, 0.09 repeating. Now, I'll show you a different way where we could write this same number in
negadecimal.
The idea is to add 1 and reverse the sequence of digits. So instead of 0.09 repeating, we're going to look at 1.90 repeating in
negadecimal.
The process of evaluating what this actually equals will be very similar to the previous example, except instead of the negative powers being even, they will be odd. That, of course, is because now the 9 is in the first place after the decimal point, whereas the 0 is in the second. So if we were to start writing out what this represents in decimal, it would be 1 plus 9 copies of negative 10 to the negative 1, and then plus 0 copies of negative 10 to the negative 2, and then plus 9 copies of negative 10 to the negative 3, and so on, with those negative odd powers of negative 10. Of course, we also have that plus 1 at the beginning. We can quickly write this out in sigma notation, leaving the 1 outside the sigma, but in the sigma, we would have the sum of negative 10 to the power of negative 2i minus 1. Let's say that, as before, we bring that factor of 9 outside of the sigma. And again, I will go from 0 up to infinity. It's worth checking that this is correct. If we plug in I equals 0, we would get negative 10 to the negative 1 times 9, which is that first term. If we plugged in I equals 1, we would get negative 10 to the negative 2 minus 1, so negative 10 to the negative 3 times 9, which gives us that next term correctly. And then, just like in the previous example, where we brought that negative 10 to the negative 2 out of the sigma, we're going to do the same thing here with negative 10 to the negative 1. Because that power is odd, this is going to be a negative number. Negative 10 to the negative 1 is negative 1 over 10. So then we can write this as 1 minus, bringing that negative 1/10 out, it's minus 9 over 10. What's left in the summation, the sigma, is negative 10 to the negative 2i. Again, this is a geometric series with the common ratio of negative 10 to the negative 2. In fact, this is the exact same series as what we saw last time. We thus know, applying the same formula, that the sum is 1 over 1 minus negative 10 to the negative 2. So this becomes 1 minus 9/10 times the value of the sum, which we know to be 1 over 1 minus negative 10 to the negative 2, which is the same as 1 over 100. Again, we're going to multiply those fractions together, so we have 1 minus in the numerator, 9 times 1 is 9, and in the denominator, 10 times 1 is 10, and 10 times minus 1 over 100 is minus 1 over 10. Continuing to simplify, we have 1 minus 10 is the same as 100 over 10. So this is going to be 100 minus 1 all over 10. In other words, 99 over 10. That's what's in the denominator. So this is 9 divided by 99 over 10. Of course, dividing by 99 over 10 is the same as multiplying by 10 over 99. So this would become 90 divided by 99. The 9's then cancel out, and so at last this becomes 1 minus 10 over 11. Of course, 1 is the same as 11 over 11, so this is 11 over 11 minus 10 over 11, giving us the same exact thing as before, 1 over 11. So just like in decimal, where we got these non-unique representations using a repeating 9, 9 being the biggest digit in base 10, we can do a similar thing in
Negadecimal.
Again, the biggest digit is 9, so we have 0.09 repeating. It's 0.9 repeating instead of just 9, because this way all of the 9's are going to land on even negative powers of negative 10, and thus they're all going to represent positive quantities. We can then express the same number by swapping the 9 and the 0. This way all of those 9's are landing on odd powers of negative 10, and thus representing negative quantities, but then we also just have to add 1. And if we do that, we get the same number expressed a different way in
Negadecimal,
which is pretty quirky. So let me know if you're sold on these negative base systems in the comments. And if you thought this was a heck of a lark, consider supporting the channel by joining Wrath of Math as a channel member. You can get early and exclusive access to all sorts of great videos, including a video where I sing a song dressed as a frog. And who wouldn't want something great and cool like that?
From my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really into it.